the first negative resistance device that we encountered in our syllabus. And what we saw there is that in the IV characteristics of tunnel diode, there was a region where the current and voltage were not, what should I say, what not in sync kind of a thing, right? So voltage was increasing, but the current was decreasing. We pointed out that region as a negative resistance region, and we saw that we can figure out also the resistance of that region by seeing how the slope varies and all. So that particular device that we learned, the tunnel diode, was based on the phenomena of quantum mechanical tunneling. I tried to explain that in as simple as possible in our last class. But there are some other devices that we will encounter one by one in this particular module, where you will see that varieties of different reasons are there behind this, how that negative resistance can arise in different devices. So another important aspect would be to understand that what is meant by this negative resistance, having negative resistance. So I will start from that notion today, and gradually we will introduce the second device that we will study. Those are called gun diodes. So let us begin. Let me just share my screen with you. Can you see my screen? Is my screen visible to you?
Yes, ma'am.
Okay. So we will today we will discuss a little bit about the physical significance of negative resistance, and from there on we will learn about this new kind of devices which are called transfer electron devices, or gun diodes to be specific. So when we studied tunnel diode in the last class, we told about this particular aspect, that in IV characteristics of these devices where we have negative resistance, we have this kind of an S-like structure. So it's either a rotated S or a straight S, but you can see that there would be a region where this negative differential resistance is present. Okay, but there could be other ways, other interpretations of negative resistance as well. So I will try to introduce two such things today. The first thing that I should talk about is phase. So we talked about the IV characteristics and all, but in terms of phase, a very interesting thing I need to point out at this particular moment, that suppose I have some device where the voltage is depicted is this graph, the gray colored graph that you can see here, and the yellow graph is the current, and both are sinusoidal, both are AC signals, and you can see that both of them are sinusoidally oscillating. We are talking about an AC signals in a particular device. So here, if I ask you that what can you say about the resistance, the effective resistance, the voltage and current are behaving like this, then you can point out one important thing, that this is time, right? As time goes on, at each and every point, as the voltage was increasing, the current was also increasing, and the voltage was decreasing, the current was also decreasing. So that means here voltage and current, if I want to plot, then I will see something like an Ohm's law like behavior, where voltage was increasing and the current was also increasing, right? But what happens if there's something like this? Here you can see that as the voltage is increasing, the current is supposed to be decreasing. And this is true for not only an 180-degree phase lag, but anything between 90 to 270-degree phase lead or lag, you will find something like this, where these two things, current and voltage, are not completely in sync, and you can conclude that here you can see something like a negative resistance. So this is something important, that how we can relate the phase of AC signals to the resistance of a device. So this notion of phase lead or lag leading to a negative resistance in a system is going to be very important, and we will study about a whole family of devices which are working on the basis of this phase differences and giving rise to negative resistance. These are called the impact family, INPAD, TRAPAD, all these devices we'll learn. So this is one important thing, that this from here also negative resistance can come into the picture. Another thing that I want to highlight is that in any negative resistance device, if I talk about the power in the system, okay, so you know that the power in a dissipated or power or generated in a particular system can be characterized by I square R, right? So I square R is the power created or dissipated in a system. So if I have a resistance and a current is flowing, I current is flowing through it, then the power dissipated there is positive. We characterize this as positive, and we calculate it as I square R, right? But what happens if this R is a negative quantity? If R is a negative quantity, then instead of having I square R, you have something like minus I square R, right? So the voltage drop across the negative resistance should be negative, and the power, instead of getting dissipated, now has a negative sign in front of it. So we can just think that this is not getting dissipated, but it is being generated from there. So this is another important notion to understand, that a negative resistance device basically does not absorb power, but it can generate power. So these devices we call active devices. These are different from other passive devices where power gets dissipated. Okay, so negative resistance devices, basically they can be used to generate power. They can be used as power generator. You can, it's one of the very important implications of having a negative resistance. Okay, so you can make microwave oscillators, power generators using these devices. So this is another point that I wanted to highlight. The third thing that I need to talk about today, and this is on the thing on which we are going to focus today, is the phenomena of charge accumulation. And for that, I have a small recording for you. So I will just try to explain as I go on, I try to explain this derivation, that the main notion of this particular idea is that if you have some charge heterogeneity created inside a system, suppose the system in any material, you have a space where some charges suddenly got accumulated. Some charges suddenly got accumulated, and what will happen to that charge? What is going to be the fate of that charge if it is a positive resistance device and if it is a negative resistance device? So that is the question we are asking. Okay, and you will understand why I am asking this question soon. So the idea is this, that you have a block of a material, and that material can have positive or negative resistance. Now, for some reason, for some unknown reason, small amount of charge got accumulated at a certain portion of this material. Then what is the fate of that charge accumulation? Will that increase with time or will that decrease with time? So if I ask this question, then we can answer this question with the help of Maxwell's equations and our simple Ohm's law. Okay, so you know that the current density J is given by, so this is just to quickly brush up some of your memories and some of the equations that you already know. And if you forgot them, just go back and look on your basic electrostatic study, and you will, I'm sure. Yeah, it's okay. So I will just. Can you see it?
Spotlighted yourself, ma'am, so you're not. Yeah. Yes, ma'am. Now it's visible, ma'am.
It's visible. Okay. So you can understand this derivation that I am doing here with the reference to Ohm's law, Maxwell's equation, and some simple electrostatic relations that you already know. So just go and brush up your knowledge a little bit. I am sure that you will be able to understand this. I'll also share this video with you so that you get an idea of what we are doing here. So as you know that J, the current density, these are all general definitions, right? The current density is given by N, E, V. N is the number of carriers present, E is the electronic charge, and V is the velocity of each of these electronic charge. So together they give rise to the current density. And Ohm's law can be also written as J is equal to sigma E. J is equal to sigma E is another form of Ohm's law. V is equal to IR. You can simply from there take a density version of that. So make current density, dividing it by the distance square, and you get J is equal to sigma E. So that is another form of Ohm's law. So our starting point is this, and we are trying to understand the question that what is going to happen if I have a charge accumulated in a certain portion of a material. So we don't know what kind of a material we are talking about, but we know that this is either a material with a positive resistance or a material with a negative resistance. So here one important term that is going to be very useful for us to understand is understand this entire question is going to be if I look at the conductance. So conductance is di dv, right? So differential conductance is given by di dv. So let us see what is di dv. Di dv will be something is equal to dj de, because these are the same quantities, right? If you consider V is equal to IR, and from there you try to figure out what the conductivity is, or you consider the other version of Ohm's law, J is equal to sigma E, and from there you try to define what conductivity is, you get these two equations to be equivalent to each other, right? So di dv is equivalent to dj de, okay? So dj de is the same quantity. Now let us use this equation that we have already wrote, JEV, to figure out what is going to be dj de. So J is equal to NEV. There I have N, which is a concentration, E is the electronic charge, V is the velocity, right? And both of N and E are constants. Once you choose a material, then N and E are not going to change. So these are constant. So if I want to see that what is dj de, if I want to see that what is dj de, then I'm going to get something like Ne dv de. Okay, I'm going to get something like Ne dv de, because N and E are constants. Okay, so V is the quantity, velocity is the quantity that is going to change with electric field. So as you change the electric field, increase or decrease the electric field, the velocity of the electrons are going to change. And what is dvde? As you already know, you have already got introduced to the term mobility, right? Mu is the mobility, and you know mu is defined as dv de. Okay, so this gives us a very important relation that di dv, that is the conductivity of the system, is basically given by Ne mu. Okay, now di dv is basically conductivity, means that is reflecting what is the resistance, right? So if resistance is negative, if I'm talking about a device where resistance is negative, okay, then Ne and mu, which one out of these three are going to be the negative quantity? Okay, so just ask yourself this question, that if the conductivity, or 1 by R, is equal to Ne mu, then which one of Ne or mu is going to be negative if I have a negative conductivity? Yes.
Ma'am, will it be mu?
Mu, right? Mu, it will be mu, right? So for negative conductance devices, I will have mu also negative. So that is a very important thing that we need to remember, that the mobility of the carriers, is going to be negative if I am talking about a negative conductance device. Okay, because the conductivity, the negative conductance is not dependent of electronic charge. That is something you need to understand, right? So the tunnel diode, there both the holes and the electrons are flowing. So E could not be the quantity that is controlling the sign of resistance. So that must be mu. That must be mu that is controlling the sign of the resistance. So if the resistance is negative, then mu must be negative. Okay, so do we understand this? Up to this point is clear, that if for a negative resistance device, I will have mu is equal to negative. Fine. Okay.
Yes, ma'am.
Okay. So this is something, a new thing that we learned. Now let us talk about the question from where we started. The question where we were asking that in a such kind of a material, positive or negative resistance, we don't know for sure, but one of these kinds, I have a charge accumulation taking place. So for some reason, in a portion of a material, a charge, some charge, that could be electronic charge or holes, depending on I am talking about a p-type or an n-type material, some charge got accumulated at a certain portion of this material. So as time goes on, how this charge is going to be accumulated further or dissipate, or it will just make a move towards a homogeneous distribution. It will move towards every side, and you will not have a charge accumulation anymore. So to answer this question, we take help of Maxwell's equation. So this is one of the well-known Maxwell's equations, which is the curl of H is equal to del D del T plus J. Explain each and every term once, but I'm sure that you will be able to get the equation in your textbooks and everywhere. So curl of H is the magnetic field, and that is equal to del D del T. D is the displacement current, or you can say that this is a version of electric current that we had just excluded epsilon from electric field, and you get this kind of a thing. So it's called electric displacement vector, and J is the current, the original current density that you have in the circuit. So this is basically telling you that how from a magnetic field a current can be created. So that this is the Maxwell equation. The 4 Maxwell's equations are there. This one is the first one that relates electric field and magnetic field together. So we start answering this question using this particular equation, and you will see why. Next step, we take divergence on both sides. So if you remember your vector algebra a little bit, I am taking divergence on both sides of this equation, and then what should I have? The del del T will come out, right? This is just a time variation. You will take divergence of D plus divergence of J, right? So divergence of J, divergence of D, and divergence of curl of H. So you know that divergence of curl of any quantity has to be 0. Any vector has to be 0. That is for any vector, that is true, right? From definition of these two operators, that is true. So I equate that to 0. I equate this equation to 0. Divergence of curl of H is equal to 0, and that makes del del T of divergence of D plus divergence of J is equal to 0. Okay, so from this point onwards, I will take the help of the equations that I have already with us. The definition of J, I will take that into account, and I will plug that inside this equation to understand further the future of that charge distribution that has accumulated for some reason inside the material. Because as you can see that divergence of D is rho, that is the charge density from the first Maxwell's equation. So the first Maxwell's equation, which comes out from Gauss's law, tells you that there would be no electric field if there is no charge, right? That is the first Maxwell's equation. That is the first law of electrostatics that tells you that if there is no charge, then there could not be any electric field. So that the electric displacement vector D that we have here is basically the same representative of the electric field. So what I am trying to do here is, using the first Maxwell's equation, I replace divergence of D using by rho. Rho is the electric charge density. And using the Ohm's law, I replace J by sigma E. I replace J by sigma E. So the equation that I am left with is del rho del T plus divergence of sigma E is equal to 0. Okay, del rho del T plus divergence of sigma E is equal to 0. Divergence of D is equal to rho, that comes from the first Maxwell's equation, and J is equal to sigma E comes from the definition, the relation from Ohm's law. Okay. Next step, we again replace divergence of E from the first Maxwell's equation by rho by epsilon. Rho by epsilon, because epsilon times E is D, displacement vector, that is how it is defined. So we are replacing that. We are replacing divergence of E in terms of rho by epsilon, and this is the equation where we stop. This is the equation that is basically telling you, this is the first order differential equation that tells you that how how rho varies with time. If I solve this equation, I will get rho, the charge density, as a function of time. Okay, so I will stop here for a moment and ask you that if you have any confusions up to this point. If you have confusion regarding the Maxwell's equations, you can just refer to any textbook, electrostatics textbook, that will explain that how the Maxwell's equation look like. Here we have used the first one and the third one of the Maxwell's equations. First one, divergence of E is equal to rho by epsilon, or divergence of D is equal to rho, because D and E are related by just a factor of epsilon. Okay, so these are the two equations we have used. Now it's a first order differential equation and you can solve it. What kind of a solution do you expect? If I have an equation like this, what should be the solution for rho? What kind of a solution should we have? What kind of a solution should we have? Exponential, right? So del rho del t plus some constant times
Yes,
rho is
ma'am.
equal to 0, right? So it should give me an exponential solution. And what would be the exponent? What would be on top of e to the power? On e to the power, you will have minus sigma by epsilon, right? So minus sigma by epsilon times t. That is how the that is how the charge or the charge density rho should change. Okay, so at any time instant rho, if you are doing the derivation on your notebook right now, then you will understand that at any time point, rho at time t would be given by rho 0 e to the power of minus sigma by epsilon times t. That is the solution of this equation. Okay, that is the solution of this equation. So at this point, if we just look at this expression, this tells you that if I have some charge accumulation at any place, if some charge got accumulated at any place and we are not influencing it anyway from outside, then with time it should exponentially decay, right? You are having an exponential decay term. On top of exponential, you have a negative term that tells you that it should decay with time. So that is kind of true, right? So in any material, if you suddenly have a charge accumulation for some reason and you are not influencing it, then eventually it should spread everywhere. That is what happens. That is kind of diffusion, right? So that is what happens. If you have a high concentration somewhere, gradually it spreads everywhere and you have a homogeneous kind of a structure, right? So this is expected normally. That is how your equation is written there. Okay, but there is a catch. What is the catch? You have here sigma by epsilon. Okay, and can I relate this sigma with my mu, the mobility? Just look at the equations that are written on top of this page and tell me how I can incorporate mu inside this exponential expression that I have, that rho t is equal to rho 0 e to the power minus sigma by epsilon times t. If I want to write down this equation not in terms of sigma by epsilon but in terms of mu, the mobility, using the equations that are written, the Ohm's law and all these things, can I do that? In the first line you can see J is equal to NEV and that is equal to sigma E, right? So from there, can I do something so that the sigma gets out of the picture and mu comes in? Can you tell me what would be the expression if I try to push mu in? If I try to incorporate mu inside, you should get something like this. That Qt or rho t, that is the charge or the charge density. Okay, the charge or the charge density is going to be something like this. So are you getting this kind of an expression? Those who are doing this in your notebook, are you getting an expression like this using the Ohm's law and the definition of J?
Yes, ma'am.
Right.
We just got it.
Got it? Okay, very
Yes,
good.
ma'am.
So you can see that instead of sigma, I can just replace it in terms of mu using just some simple algebraic manipulations. You can do that. I trust you on this. So if mu is sitting there, then the picture is a little bit different, right? As far as sigma was there, we were not concerned much. But as mu came into the picture, we now know that mu is negative for all the negative resistance devices. So if mu is negative, then this exponential term, instead of being an exponential decay that should vary with time, like it is degrading, it should be a positive sign. If mu is negative, you just put the value of mu and it becomes a positive exponential, and positive exponential grows, right? So that simply means that if inside a negative resistance device, if this block, this chunk of thing that I have here, the material that I have here, if it is a negative resistance device, a very important statement I am making here, if you have a charge heterogeneity created for some reason, for any arbitrary reason, if some charge heterogeneity comes into the picture, you suddenly have an accumulation of some positive charges at some place, then eventually with time, that should grow. That will grow exponentially. A very important statement. That basically makes a high charge domain inside your material. That basically creates a domain inside which you have this huge amount of charge accumulation. Okay, so this is called high field domain. That is a very, very important property of any negative resistance device. And interestingly, all this derivation that we did, we never considered any PN junction, right? We just talked about a material where negative resistance is there. That means that if I just have not any junction, just a chunk of a material, and for some reason, if that material has negative resistance, then I can have this charge accumulation inside this material. Okay, so I guess this idea is, I tried to convey this as mathematically as possible to you. I guess it is conveyed, and I guess you understand this by now. So based on this very important notion, the other family of negative resistance devices that we are going to discuss next, gun diodes, will work. Okay, so gun diodes are basically called transferred electron devices, which are fundamentally different from other devices that we have learned so far, because these have no junctions inside it. No junctions, just one bulk of one particular material, either p-type or n-type. Okay, no junctions, just one chunk of a material, either p-type or n-type. But they are fabricated from very, very specific materials. And why so? We will discuss that in detail in the next class. These are the compound semiconductors, which I guess sir has already discussed about in your other section of classes, gallium arsenide, indium phosphide, these kind of materials. And why so? We will talk about that. But these particular devices, gun diodes, which are called transferred electron devices, are fundamentally different from these particular aspects, that these are bulk devices without any junctions. These can be made only with certain semiconductors, and these work with electrons which we call hot electrons. Okay, the electrons that we usually have, we call them warm electrons, which are equivalent energy as room temperature. So room temperature is T. You multiply it with KB, Boltzmann constant KB, you get some energy equivalent of that. So if an electron has that much energy, we call that a warm electron. Okay, so our usual PN junctions that we have, they work with electrons, they function with electrons which have that much of energy. PEDs, this particular material devices that we will discuss from next class, gun diode, they work with hot electrons. Their energy is much more higher than the room temperature thermal energy. So gun diodes invented by J.B. Gunn, which has just some metal contacts on both sides and a single type of material sitting here, no PN junction. Okay, you can have a single type of material present here, no PN junction there, just two metallic contacts for two terminals on both sides. This is the symbol of gun diodes, and how it works, how it functions, what is the working principle, why do we need specifically some compound semiconductors, all these details we will discuss in the next class. Okay, so today's class was mostly mathematically incorporating the idea and further deeper understanding of negative resistance and distinguishing between the different types of negative resistance that we have. Yes, yes.
Ma'am, could you go to the TED slide once, ma'am? I didn't.
Yeah, definitely. Yeah. So these are the three important, if someone asks you that why transferred electron devices are different, in which aspects, these are the three important points that you should mention. Okay, bulk devices because no junctions, particular semiconductors, compound semiconductors, very particular choice of semiconductors. You cannot make them using silicon, germanium or something like this. And the third one is they operate with hot electrons whose energy is much higher than the room temperature thermal energy. Okay, so these are the 3 points. And we will talk about in detail, we'll explain each of these points and that why these points are so important. We'll talk about an entire theory about how these devices function, okay, in the next class. So I will stop here at this point today. We'll start from this slide only in the next class and talk about in detail about gun diodes. Okay, so if you have any questions, you can please ask. Okay, so I guess you don't have any question. I will just request you to go back and have a quick look at the derivation that we did today. Okay, so let me know if you have any confusion. Just get some reference to basic electrostatic equations and the Maxwell's equations, and I'm sure you will be able to understand it with the very basic understanding of vector algebra. Okay, but still, if you face any problem, we can discuss that again in the next class. So I'm stopping here today. See you on the next class. We just have 2 devices left in our